Hi, I'm going to talk about mapping, which has to deal with reinterpretation of values. So we're dealing with the node editor where, it's the wild, wild west of things that we can do. So I can have a position, the position of an object driving the color of a surface. I can have a texture image driving the scaling of some instances. So there's all these possibilities of connections that I can do here, but just because I can do them doesn't mean that they automatically make sense. So I'm going to look into routines that deal with conversion, filtering, following, blending, things that many times are the middleman between the data values that we have and the operations we are trying to do. So here I have here two examples. I have a displacement map, and usually these maps are baked into a unit range. So if we had negative values, or if we had values above 1, it would be hard to inspect what's on the map because we would have black clipping and we would have white clipping. So they are usually baked into a unit range, so it goes from black to white. But then we're given many times a scaling factor, and this scaling factor is to be used to rescale the unit range into the negative and the positive of that scaling factor. So with this, not only the values of the map get the correct magnitude, the correct height, but they also have the correct sign. So negative values will make my mesh displace inward, and positive values will make my mesh displace outward. Another example is many times you want to create exposed parameters that are easy to interact with, that control other things, that something is that control other aspects of an operation. So for example, here I have this eye, which is being controlled by this control object. As I move it up to 1, it opens the eyelids. As I move it up to -1, it closes the eyelids. So here I'm having this -1 to 1 corresponding to the eyelids opening up or closing. So what things we are going to look at is these middle operations here. So you can see there's this sense of input and output. And this is something that is it's very basic on how many nodes work. You have some input value, something is done to that value, and from that you get an output. And many times it's useful to not just see what happens to a single value, but what happens to a collection of values. So that's when we get into graphs. So graphs are like visual representations of the relationship between input and output. So they are useful to check what happens to the output as the input progresses, as the input changes. And so we have here this 45-degree line, which is basically a neutral line where the input is equal to the output. But usually we have a line or curve that we have some input value, we check it against the graph, and then we get the corresponding output value. So these lines or curves, they're not geometric lines and curves. So the x value is evaluated not along the graph, but on the axis. And they also have another rule in which that each input value has a single corresponding, single matching output value. So you won't see loops like this, or you won't see vertical lines, because it wouldn't make a lot of sense, say here in the graph editor at frame 20 to have all the possible, values, for say in this case, for a position of an object. So for each input value, there's a single matching output value and nothing more. So here I have a collection of graphs, and here I have an example of the graph editor, which is probably the place where you are more used to see graphs. And here it's pretty obvious, right? Here you're mapping frames, mapping time to motion channel values. And so you usually manipulate just these control points, but the graph allows you to grasp what happens in between those points. And that's very important because you can easily assess what's the easing, what's the transition between those keys, and you don't need to do a preview to just check what's going on in there. So here I have other examples of graphs that usually you don't see them represented. We see graphs represented here in Lightwave in function nodes, sometimes also in curve nodes, but other than that, the linear remapping nodes don't have them. So I decided to just make here some visual representation of that. So here there's the neutral line in which the input is equal to the output. So there's no change was done to the values. And here's an example of the equation of a straight line. So the equation of straight line is basically the compound we've seen before, the transform 1D, but written in another way. So usually the equation of straight line straight line is written like this. This is the slope, which controls the inclination, the angle of the line, and this one is the intercept. Basically, it defines where the line is going to intersect the y-axis. This linear, this equation allows me to do any linear conversion that I need. So with this alone, I can already, for example, do this displacement map example. I can solve it with it. The issue is that many times it's not very rational to use it. So let's look into it in Lightwave, and let's see what we can do about this one, for example. So here in Lightwave, I have a setup with instances to graph things. So I have an array of points, 2001 points, and in it I have an instancer, and I'm using the base position of the array, so the X position, and I'm mapping it onto the Y position. Offset. So if nothing is done to the value, you can see that I have that neutral line in which the input is equal to the output. But then I can start do things like, for example, I can let me use the power function. So say I have 2 to the power of 2. I can turn on the input SPI, and I can see that the value is 4. But what if I want to see what this function is doing, not just to one value, but to many values? So this is what this setup is useful for. So I can plug this in here and plug this in here, and now I can see I have this shape, this parabola. And I know that quadratic functions have this shape, so okay, I can immediately recognize what type of function it is, what's doing to the values. So here I'm going to use it to show the transform on D compound in use. So I have nothing done in there, but if I do say 2, I scale the values by 2. Now I see that the output values grow bigger. If I do 0.1, now they go flatter. And as the input changes, they don't change as much. If I say translate the values by 2, you notice that they now intersect the y-axis on 2, or if I put say -1, now they intersect on -1, etc. So since with this compound alone, I can have any linear conversion that I need. So that's nice. Usually, many times you'll see that I'll use objects in the scene to manipulate setups in the node editor. This is because it's very annoying for me to click nodes to check what's going on, and it's a bit cumbersome. And I would prefer to say I have this item info node which has object A in there, which is this object here, and I much rather have say the Y position of this object plugged into translate and the Y scale plugged onto scale. So now when I move this object up and down, you can see that I can basically do the same thing I did with the constant nodes, but in a much more interactive way, much faster. So you can see with this, I can have any straight line that I want. So the issue with this type of linear conversion is that many times it's not the most reasonable way to go about it. So say, for example, I have this object here, and I want to fit it between these two yellow rectangles. So I can scale and translate, right? I can come here, scale, translate, and I can kind of try to grasp what's the what should I do, what's the actual scale and translation this needs. And so this is a bit cumbersome because it focuses on center, and you notice that it's hard to get in there. So I much rather have something like the box tool, in which you have these handles. You have the start and the finish of the box, and you put them where you want, and everything in between gets the same relative position. So this is a much more easy way to define what I want. So the same thing will be true for a linear conversion, where many times it's easier to define a starting point and an end point than trying to use geometric transformation. So this is where the two-point linear fitting comes in which we define an initial range and an input range and an output range, and it makes it much easier to define conversion. So let's look into this example of the displacement map. So I had here that I wanted to go from 0 to 1, that I wanted to go to minus 3.51 to 3.51. So if I do this with the transform node, I need to scale it by 2 times 3.51. So this times 2, and I need to subtract here in the translate minus 0.351. So with this, the input that goes from 0 to 1, which is my initial range, corresponds now to minus 3.51 to 3.51. But you notice this was a bit finicky, to double that value and then subtract. So a bit strange. Unlike, say, with Remap node, where I can just basically input these ranges. So I can say that I want to go from 0 to 1 to minus 3.51 to positive 3.51. So with this, I get the same exact result. If I put this in here, if I put this in here. So you can see that it's the same exact result with the straight equation of a straight line, but it's much more rational to work with, because I actually defined my in point and out point very easily. So this operation is going to be, I'm going to break it down into steps, into smaller operations, so we can look into what those operations allow. So here I have the same setup, but the input minimum and maximum and the output minimum and maximum are controlled by these two objects. And we can see that it's very easy for this operation to limit, to kill off, to cut off the extrapolation. So the values that are in between the two reference points, they are interpolated. The values that are beyond those two limits are extrapolated. So when we clamp the values here, we are basically denying extrapolation and just keeping the interpolation. And so basically I have this compound that is a remap example that tries to mimic what remap is doing, just for the purpose of looking into what we can observe here in the steps of the operation. So first I'm going to look into those in here. So first we have normalization here with box step, then we have linear interpolation here with a mixer, and I'm going to look into other nodes like the gradient, position delta scaling, etc. Here there's some some equations of these, etc. So I'm just basically going to break down this whole operation into smaller steps and see what we can do in between. So one interesting thing that we can do is already shown with the clamp. Another one, and it's going to be another section, is to take care of this interpolation between the two reference points. So we can introduce functions in between these two operations. So between normalization and interpolation, can introduce a function, and with this we get, instead of having a linear transition, now I've made a function to fit between those 2 points, or I can also have a curve and I can fit a curve in there. So it's very handy. And another thing we're going to see with the curve is to have a custom mapping. So something I'm going to build a constraint so that with the curve I can constrain the motion of something really precisely. And the last thing I'm going to look into is the parameterization of a simple function. So here we have the sine function. And by doing some conjugation, transforming the input before and transforming the output after it goes through the sine, I can have a control object. So here I'm also using this item A motion channel information to manipulate those two operations, and I can control the shape of the sine function and what goes on. So I can control the amplitude, I can control the phase, the frequency, shift, etc. So this is very useful. So even though these things I'm trying to show them in the viewport, so it looks, so we can look at them. Many times, these are things that you are not going to see in the 3D viewport. They are control parameters. They are things that are going to be used, but you are not actually going to see them. And it would be kind of wrong at times to try to make geometry out of them, because they become so skewed that they become, even though they seem like something that you could use to displace a mesh. At times, since the displacement here is just happening on the y-axis, it's going to create a shear effect, which sometimes you want, but many times that's not exactly what you want for a geometry configuration. So many times for geometric shapes, etc., you prefer something that is evaluated along the shape, unlike in here in the graphs where things are evaluated along the axis. So these are the things I'm going to look into. I'm going to start off with the 2-point linear fitting.